In this and in the next few videos, we're going to be looking at aromatic compounds, and in particular, we're going to be looking at what makes a compound aromatic. Our quintessential aromatic compound is benzene, so that is a 6-member ring, and it has the alternating double and single bonds. What we notice about this compound is that it has a bond order of 1.5, and the bond lengths are the 1.397 angstroms, which is actually slightly smaller than in the conjugated compound like this butadiene, and it's quite a bit smaller than the single bonds in the conjugated compounds. And so each one of the bonds in one of these is actually a 1.5 bond. And so that's why we can draw it as the resonance representation, but a popular way of showing this is what's called the combined representation. And this is drawn with a circle inside, and that's because we don't actually know which bonds are single and which ones are double because the electrons spread out through the entire ring. So we can actually think of those like electron density forming these donuts above and below the plane of the ring. There are multiple different types of aromatic compounds that we will be looking at in the next few videos, but not everything that has the alternating single and double bonds are considered aromatic. So for instance, this cyclooctatetraene here is not aromatic, so we don't actually have the resonance here. Same with this cyclobutadiene. What we'll notice in the next few videos is that there are multiple ways for something to be either aromatic, non-aromatic, or anti-aromatic. But in this video, we will continue using the benzene as our illustration. So in addition to shorter bond lengths, one of the things we notice about the bonds in something like benzene is that they are quite a bit more stable than what would be predicted. So if we have the energy of just the cyclohexane down here at the bottom, then we can look at what happens when we add a double bond into this. So that makes the energy go up by 120 kilojoules per mole. Then if we add another double bond, it goes up to 240. So we've just added another 120 to it. Then if we add conjugation to it, so something like this, then instead of being exactly where the other one was, which if there wasn't anything like conjugation is where we would predict that to be, because all it is just 2 double bonds, it actually goes down slightly. So it goes down by 8 kilojoules. So that is the resonance energy. And so it's slightly more stable than this compound here where the double bonds are not conjugated. If we add yet another double bond, so we get to 3 double bonds, it's predicted to be about 359 kilojoules per mole. But what actually ends up happening is it goes down to here. So it's actually even lower than just the conjugated system here. And it's down by 151 kilojoules. So that's quite a bit of resonance energy. We can think about this somewhat more mathematically looking at it down here. What this shows is that if we completely hydrogenate our benzene here, then that will give off 208 kilojoules per mole. So that is an exothermic reaction. But if we just do this to 3 cyclohexanes, so we're just 3 non-conjugated double bonds, that's 359 kilojoules per mole. And so that is a difference of 151 kilojoules per mole. And so that is where that resonance energy comes from. And so again, what we see for benzene is that completely hydrogenating it gives off 208 kilojoules per mole, whereas if we do that to the 1,3-cyclohexadiene, it's minus 232 kilojoules per mole. So the 1,3-cyclohexadiene would just be this right here. And so if we want to completely hydrogenate that, so essentially turning it into this up here, then that will take 232 kilojoules per mole. And so we see we are giving off less heat when we completely hydrogenate the benzene as opposed to the 1,3-cyclohexadiene. And in fact, it's about 24 kilojoules per mole less energy that is being given off. And so that's because that first bond that we have to hydrogenate, what's being shown right here, is going to actually be endothermic and require us to put energy into it because it's such a stable bond. Another important thing to remember about these benzene rings, and this is something that will be important in later videos, is that they don't actually undergo the same reactions as our normal alkenes. So if we have something like the cyclohexene right here, we can oxidize that into this diol right here. But if we try doing the same thing with our benzene ring, there will actually be no reaction. Similarly, if we try to halogenate this cyclohexene right here, we can add the bromine right there and right there. But if we try to do the same thing with our benzene, we will get no reaction. As I said, in future videos, we'll look at what reactions we can do, and one of the important ones is what's called the electrophilic aromatic substitution. And so what is different here is we have this Lewis acid, and we're only going to be putting a single bromine onto this. So instead of ending up with this right here, which is what you would expect if these were just behaving like normal double bonds, where we are doing this halogenation, we will only end up with a single bromine on here, and then this HBr will be given off as a gas. And like I said, we also need this Lewis acid right here as a catalyst. And one other thing I wanted to talk about in this video is the aromatic rings and their resonance. If we start putting on these different substituents onto our aromatic rings, then we can actually get different reactions. Again, we will look at this in a lot more detail in future videos, but we can categorize these types of substituents as either electron donating groups or electron withdrawing groups. So electron donating groups will have the aromatic ring, then it'll maybe have an ether, or it'll have an amine of some kind. The electron withdrawing groups usually have something with double bonds in it, like this carbonyl, or this cyano group, or this nitro group right here. There is also the halogens we can put on it. Those have a little bit different of an effect. Again, we will talk more about that in future videos. The way we can think about this is if we have an electron donating group, such as this hydroxyl group right here, we can have resonance. So this lone pair can come down here, and then this will go up here and form a lone pair on the ring. So we end up with this, then this can come down here, this can then go over here, so we have a lone pair right there, then this can come down here, this can go up there, so we have a lone pair like this on here. Then this can actually come back down here. This can go over there, and then we just loop back around to what we had over here. And the thing to notice is, one, that we have these lone pairs within the ring in our resonance structures. So that's why it's an electron donating group, because we are actually adding more electron density into the ring. The other thing to notice is that it is on these particular carbons right here, and right here. So they will not end up on that carbon or on that carbon. This will become very important in later videos when we start talking about the reactions of these compounds. But for now, just notice that it is those three carbons on which the lone pairs are going. Then if we look at something that is an electron withdrawing group, such as this nitro group, now what we can do, we can have this go up here. So those electrons from that double bond go there. Then these will go up onto this oxygen. So we end up with this right here. We have the positive charge on that carbon, then we can move this over here so that we end up with a positive charge there. Then we can have this move down here so that we end up with this. Again, we can have this come down here, then this go over there, so that we just recapitulate what we started with. And again, the two things to notice here, one is that now instead of lone pairs, now we have positive charges. So we've actually lost electron density in the ring. That's why it's called an electron withdrawing group. And the other thing to notice, again, is that they are on these three carbons. Again, we aren't talking about in this video yet why that's important, but it is important, so it is something to notice and keep in mind. And then we can look at this figure here, which just shows us the electron density in these different compounds. So we have the benzene here. We can see what the electron density is in there. And if we add the phenol, which is an electron donating group, we see the electron density there shown in red is a lot higher in the ring. If we have this benzaldehyde, which is an electron withdrawing group, we have a lot less red in the ring right there because we've pulled some of the electron density out of the ring. Again, when we have the halogens, it does something a little bit different, which we'll talk about more in future videos, so I won't go over that here. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.